Thank you very much. Okay, so those of you that have attended a talk on base extension semantics or any sort of proof theoretic semantics before, I hope this helps. That's all I can say. A lot of us, I feel like for this topic, we should really have 2-hour talks, and we should start from a very simple question, which is, what is a semantics? Alas, we don't have time, so we will just continue and hope for the best. So what is the point of today's talk? Well, it's to give an overview of the original sort of base extension semantics for IPL. So we're going to be retreading old water. But the purpose of that is to really show two things. Firstly, how simple the original idea was, and secondly, just how easy it is to expand it to something a lot more complicated. And the system that we will expand it to are the intuitionistic modal logics that were presented by Simpson in his thesis. So we'll obviously give a little overview of that as well. Now, when I talk about the logic, really what I'm talking about is derivability in the logic, but semantics. Oh, no, actually semantics. And then we will, of course, talk about how to adapt what we go over. Okay, so very briefly, the point of base extension semantics is that we kind of build a consequence relation. We have a consequence relation which induces sort of a notion of atomic derivability relative to some rules, and those rules are what we call a base. Okay, we use that as a base case of a satisfaction relation, which we use to then give meanings to formulae. Okay, now why this works is a long discussion, so we won't go into that. But soundness and completeness is, very importantly, the same as it's always been. Okay, so like I say here, showing soundness corresponds to showing that kind of every inference figure, every possible inference is valid, and showing completeness is that every valid sequence is also derivable. Bless you. So, NJ, we're all familiar with NJ. It's a nice and simple proof system. It's natural deduction for intuitionistic logic, propositional intuitionistic logic. But what are some features here that we have that are common? Okay, so this is a question that we need to always ask, because if we want to sort of understand the sort of build a proof theoretic semantics, we want to build a sort of atomic system that behaves similarly or similarly enough to be able to capture the derivability in the logic without necessarily talking about the formulas of that logic. So what are some common properties here that we have? Well, we have hypothetical proofs. Okay, we have multiple hypotheses. So really, there's nothing that prevents us from considering sort of a very general inference figure. Okay, and so I call this the general inference figure. And so this is what I would consider the general inference figure for NJ to be. So capital gammas, or generally capital Greek letters in my talk will refer to sets of formulae. Lowercase Greek letters will refer to individual formulas. And then the same thing for Latin letters refer to atoms, propositional atoms. Okay, so here we have hypothetical derivations, many. These gammas could be empty, and we need all of these to be satisfied for us to be able to conclude what's below the inference line. So that's the idea of what the general inference figure is. And you can see how this is a real generalization of all of these figures, right? Sort of if I want to sort of create a single thing, scheme, whatever, that represents all of those rules, we could say it's this, and then we say we instantiate this with certain conditions or certain cases, and they give us all of NJ, okay? And obviously then derivability follows suit, okay? So we have a notion of derivability. So if we suppose a formula is in gamma, then of course this notion of derivability holds automatically. But then if we have a general inference figure, our notion of derivability is as follows. If each of these derivations holds true in NJ relative to possibly a set of other assumptions, then phi holds relative to that set of assumptions in NJ. And you see that this gives us an inductive definition for a derivation in NJ. And this is very important because this is, one might say that what I'm doing here is applying the rule in derivation. And we'll see in a second that this is a recurring theme in base extension semantics. So why am I talking about all of this? Well, because we want to atomize everything. So base extension semantics doesn't talk about NJ, or doesn't use NJ as a sort of object in which to construct its models, but it uses bases with rules purely in terms of atoms, not in terms of formulae, purely in terms of atoms. But like I said, we want these rules and we want these derivations to be as similar as possible to what we have in NJ. This will come back, this will be very important in the completeness argument, especially. And so you see that we have a notion of a general inference figure with atoms. It's exactly the same as what we had before, but now we restrict it to atoms. We have a linear notation that I really like using. And we can give some examples of these atomic rules. This would be an atomic axiom, okay? We know this is true. Another thing we can do with atomic rules is give definitions to things, okay? So excuse my pronunciation here, but we have 3 rules here. The first rule says that if Freyja is a cat and Freyja is female, then Freyja is a leða, okay? That's the Icelandic word for female cat. But we know that from these 3 definitions, because if I have a system where only these 3 rules exist, and I say to you, Freyja is a leða, from the assumption that Freyja is a leða, I conclude Freyja is a cat. From the assumption that Freyja is a leða, I conclude Freyja is female. And from the assumptions that Freyja is a cat and Freyja is female, I conclude that Freyja is a leða. I therefore know that I can sort of associate the meaning of the word leða with the fact that something is a cat and something is female. Okay, well, you know, there's always a thing of, well, quantification, instantiations of you know, what is Freyja, blah, 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 but we'll ignore that for now, okay? So just the meaning of the word leða, we can see that we can obtain this meaning through this, effectively. So this isn't completely insane. There is something here. Another thing we can do, which is a little bit crazier, is, for example, since we are computer scientists, define what a byte is, for example, right? The data type, byte. Okay, this is 1/2 of the definition. Okay, we say that if var1 is a byte and some phi follows from the fact that var1 has value 0, var1 has value 1, blah, 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 all the way up to 255, then we can conclude that thing. And then the other rules, which I haven't put up here, is that var1 has value 0, therefore var1 is a byte. var1 has value 1, therefore var1 is a byte, all the way up to 255. This set of rules also gives me the definition of a byte. And here we're doing it with hypothesis discharging, right? So hypothesis discharging is a real thing. These hypothetical derivations, they really do assist in allowing us to derive meaning, okay? So what are we going to do with them? Well, first thing first, we need to set up some tools, technology. And we're talking about bases, base extension semantics. So the definition of a base is just a set of these atomic rules, okay? And then we define a notion of derivability in a base. And if you notice, this is exactly the same notion of derivability that we had for NJ, except here, rather than being relative to the rules of NJ, natural deduction, we have that we are applying rules from the base, okay? So we have a sort of atomic notion of derivability, and we can use this to give us semantics. So let's give us some before we do that, let's look at some example derivations. So if I have a base with these rules, okay, so it's maybe a bit hard to read, but it says that if I have the fact that A is an axiom, and I have that from A and B I can conclude C, then it should be the case that this is derivable, right? Well, here I apply this rule, and I get this. This is by reflexivity. Here I apply this rule with A, it's an axiom, so anything on the left-hand side, we can ignore it. So this is an atomic derivation. I can give a more complicated example as follows. We can stare at this all day, but it works, I promise you. It's a good example, though, because it shows how hypothesis discharge actually appears in atomic derivations. And this is the semantics. Now, who can tell me what's weird here relative to something like Kripke semantics? What's different? Somebody that doesn't deal with proof theoretic semantics. Yes. Disjunction, thank you. Disjunction is weird. Disjunction is conjunctive, which is seemingly a bit crazy. Now, this is interesting and is a key property of base extension semantics. Or rather, it's sort of, what makes it kind of unique, really, is that disjunction has this kind of behavior. The reason why this is, again, kind of complex. Don't have enough time to go into the details. There's a lot written about it, but it will come up later again. But it will come up in the context of diamond, as we'll see. But these are the clauses, and it's not super crazy. And as we can see, the sort of satisfaction relation for atoms is that it's atomically derivable in the base. So that's why we needed to talk about atomic derivations, because that's kind of the base case of our sense of meaning. Okay. So soundness and completeness. It's very important that we understand how this generally is proven. So this is still for IPL. Statement of soundness says that if the sequent from gamma I conclude phi is NJ derivable, then gamma proves phi is valid, right? So from gamma we conclude phi is valid. So this is a statement of soundness, and it's proven quite simply. We kind of do an induction over the structure of the proof itself. Okay. Completeness is a bit more interesting. So a couple of talks ago, we were talking about using atoms to simulate formulae. It's kind of, we do a similar thing here, okay? So to prove completeness, we construct a special base, and we simulate the sequent by assigning to every subformula of that sequent a particular atom. And then we construct, so that special base then has every single rule of natural deduction, but instantiated with every single one of those atoms. And each of those atoms is in every single position of every single rule, right? So we basically allow for every possible combination. Bases don't have rule schemas, bases have instances of rules. So we need to do this kind of instantiation. We have to be careful. So top and bottom need special treatment, but that's very, very easy to handle. So how do we actually prove completeness? It's actually really trivial, relatively speaking. There's three lemmas that we need, which are the three statements I have up top. The first one we call atomic soundness and completeness. I mean, this should hold true. It's not controversial based on the definitions that we've given. It says that if L proves P in a base B, then L must be able to derive P, rather, or P is derivable from the assumptions of L. We have that if B, so if phi is supported, so that's what we call forcing. We say if phi is supported in a base B, then the atom that simulates it must also be supported in the same base, and vice versa. And then we say that if this atomic derivation holds in our simulation base, this special base which does the simulation, then its translation is a correct NJ proof. And then the proof is just those 4 points there. Okay, so first statement is that of monotonicity of the satisfaction relation with respect to bases. Second point is that, well, we therefore get from this that the simulant is also holds true. Therefore, we have this derivation, and therefore we get this thing. Well, these things are inverses, so therefore we obtain our derivation. The point being, the simulation base actually allows us to simulate proofs in NJ. Very cool, very interesting. So, yes? Just the guy that came up with it chose it. I really don't know. I mean, there is an alternative argument, sort of alternative notation that's being used now, but I like the classics, and by classics I mean 10 years ago. Okay, so intuitionistic modal logics now. So is everyone okay relatively with so far what we've had? More or less. Okay, cool. So how much time do I have?
16 in total.
Brilliant. Okay.
Questions.
Okay, cool. This shouldn't be too bad. Okay, so modal formulae. So we're going to go to intuitionistic modal logics. Modal formulae are modal formulae. They're exactly what they've always been. We're not going to, think about them too much. But we need to introduce a new class of objects. Something we're going to call labeled formulae. Most of us have encountered. We have these things before. We have an intuitive, not intuitionistic, feel for what they should be. We write them like I have there, and they kind of the label kind of represents the set of worlds at which that formula holds true. So we think of it as a kind of locale. Sorry? Yeah, they're variables. So these x's are variables. And we allow for a binary relation between these variables, which we write as that. Okay. Now, a notion of atomic formula has to be subtly modified. Atomic formulas are now either propositional atoms with a label or these relational assumptions. We have a notion of a modal sequent. Sequent is an object like that. And I had to introduce an object called an extended sequent, which is just a normal sequent or possibly something of that form. And we'll revisit that in a second. So frame conditions. Now, we all do modal logic. We've all touched modal logic at some point in our life. We understand that frame conditions are the way that we usually understand the sort of restrictions on the Kripke models in a normal semantics for modal logics. These frame conditions are quite interesting because in what follows, we will always fix an arbitrary set of these frame conditions. Note the relational properties. These will come back to haunt us later. And actually, for me, one of my main criticisms of this work that I've done is how we handle the relational properties. And I have a kind of solution, but we'll talk about that later. So this is the modal logic as introduced by Simpson in his thesis. This is just one part. There's 3 slides. This is the normal sort of propositional fragment. There's nothing too special here, except for it's just worth noting that disjunction, elimination, you see that we start from a label X and we conclude with a label Y there. And the same thing happens for bottom elimination. This is necessary. This is nothing too surprising. Then we have 4 rules which govern the modalities. Introduction, elimination, pairs, but with side conditions. Okay, so box introduction has this side condition that the label Y is different, and diamond elimination has the same condition, that Y is different to the other labels. This is going to be the key difficulty in constructing the base extension semantics for this family of logics, is how to capture these side conditions. Similarly, if that gamma is non-empty, so that gamma has some of those frame conditions, we also need to add these additional rules to our proof system, right? So if we have the D axiom, then we have to add the RD rule. If we have the 2 axiom, we have to add the R2 rule, and so on. And again, R2 and D have R2, D2, that's funny. Both of those have to have those side conditions, okay? So again, general inference figure, same thing as before. But there is a problem. Or rather, there's an interesting thing to note. Observe that in none of these rules do we have a derivation which concludes a relation. Furthermore, anytime a derivation appears at the inference line, there is nothing above it. We don't discharge anything above it. We reflect this in our notion of the general inference figure, as thus. This is a technical requirement because you just get a nicer proof system. Absolutely, that's it. I chose to do this way because this is what Simpson chose to do. However, it is possible to sort of relax this requirement, and things will still work out. It's really not a problem. But it felt nicer to stick to what was done in the past. So that is to say, if this is a relational assumption, then this must be empty. If relational assumptions can always feature in here, but if this is a relational assumption, then all of these must be empty as well. So those must not exist. So now derivability. What is derivability? Things get a little bit more complicated. We need something to keep track of the worlds. So I said worlds, I shouldn't say worlds. Something to keep track of these labels. We need something to keep track of the relations between them. We use a graph to do so, okay? And we still have exactly the same rules. So we have that if this formula appears in here, then that's true. And if here we have the same thing for the relation. So if the relation is in here, then that's true. And again, exactly the same thing with the rule application. Key difference, again, this rule application must satisfy the side condition that I previously mentioned, which is, to remind us, that. But there's an additional thing that I must add, is that also that delta must also not contain any additional relational assumptions in the same way that theta does, big theta. Okay, so what do we do in the paper? Well, we only really consider the trivial graph. What we do can be extended to consider more fanciful things. But Simpson doesn't need to, and we don't need to either, because although Simpson does actually do it, but he states he doesn't need to, and he's right. We don't need to, because what a theorem is effectively if a derivation holds in the trivial graph, okay? And so the extension is not so difficult. All you would do really is consider the trivial graph by taking the non-trivial graph, taking all of the relations and putting them on the left-hand side, effectively. So, as before, atomic rules, same thing, same restrictions. We have atomic derivability, exactly as before. Although some of you might notice that ref and app are really high up on the page, so something's about to fill up the page. And that thing is this mess. And as you'll notice, these are just basically those frame conditions encoded at the level of atomic derivability. Remember, bases do not have schemas. They have rule instances. We need to hard code the frame relations for all of these labels. And so the way we do it is by effectively adding them on to the atomic derivability relation. This is harmless, philosophically a bit questionable. There are alternatives to this, and I can discuss that if somebody wishes to. The definitions follow as suit. It's not super difficult, sort of super hard to understand. It's very similar to what we had for IPL, and nothing here is too surprising. I mean, of course, we have this as well. Strictly speaking, that's not necessary, but just to make things clear, we add it as well. The rel clause, that is, and the modal cases. And as you can see with the modal cases, box is not surprising. Box is what box always is. Diamond, however, is universally quantified. Oh, that's odd. Diamond universally quantified? What's going on? Well, disjunction is usually disjunctively defined. When something is existentially defined, it's also disjunctively defined, right? That's what diamond is usually defined as. It's the same thing. The reason why the diamond clause is like this is exactly the same reason that the disjunction clause is the way it is. This seems to be a feature of proof theory, or of base extension semantics more generally, that when something in Kripke semantics is disjunctively defined, in the base extension semantics, at least how we're doing it, it tends to be conjunctively defined. This is quite interesting, and it has some nice properties. Sort of things become a little bit easier to prove, I think. You don't have to construct a witness. So soundness follows exactly the same way, but like I said before, care must be taken because of the side conditions. Okay, so we have to make sure that we adhere to the side conditions. So this kind of demonstrates that. So we just have to be really, really careful that that our proofs do adhere to the side conditions. Completeness follows pretty much in the exact same way as before. However, now we have to be careful again, because remember in the definition of atomic derivability, we have these cases. We have to make sure that anything that holds according to this still holds according to the same rule in the natural deduction. So if we're simulating something, we're simulating it correctly. Turns out it does. It's not, that part's not super difficult to do. And that's it. And that's a very, very brief overview of the work I've done on intuitionistic modal logics. So I'm happy to answer any questions.